Pessoal, nós vamos para início da aula Magna. Não, mas o microfone é para o pessoal aqui. Não é para vocês, não. Vocês vão ter que ver. Bom, tem também. Eu não conheço aquilo dentro, mas suspeitei que tivesse. Ótimo, André. Muito melhor. Bom, pessoal, nós vamos dar início aqui à aula Magna. Início do semestre PPGETI. Eu vou fazer as honras da casa, já que eu inventei essa história aqui. Aproveitando a vinda do meu queridíssimo amigo, o professor José Príncipe, é uma oportunidade única. Ele veio no contexto de uma visita ao UFC, conheceu pesquisa em inteligência artificial que nós fazemos aqui. Já visitou os laboratórios, hoje já está na visita. Eu vou me estender demais também. O currículo dele está disponível na internet. Eu só quero que vocês acreditem em mim. É o pesquisador de uma envergadura internacional. O professor Carlos Príncipe, professor da Universidade da Flórida. Português de nascença. Mas eu acredito que a palestra vai ser em inglês, pelo fato de ser uma palestra internacional. Esse momento é muito interessante. Eu queria também destacar isso. Vou aproveitar aqui e passar a palavra aqui para o nosso vice-coordenador, está apresentando a coordenação do nosso programa de pós-graduação, o professor Yuri. Obrigado, Yuri, pela presença. Obrigado a todos que estão aqui presentes. Muito interessante ver um programa cheio, momentos em que a gente priorizava reuniões remotas. Mas o momento vem a calhar, porque nós fomos recentemente agraciados com a nota máxima da CAPES, nosso programa de pós-graduação, nota 7. São pouquíssimos no Brasil, só tem 6, para você ter ideia. Então, nós somos o programa, era no 6, agora com você, virou-se de nota 7, com presença internacional do Estado, segundo a CAPES. Essa nota é atribuída a programas que são possibilidade para que tem aluno da graduação também, esse ingresso, talvez a dimensão dessa nota, excelência internacional. O programa de excelência internacional, você viu um pouquinho disso ontem, anos de colaboração com a França, a Alemanha, os países aí, menos nos Estados Unidos, mas talvez, quem sabe, só vindo seja provincial. Esse momento também me deixa particularmente feliz, porque pela coincidência, porque o seu Príncipe vai falar informalmente sobre o currículo dele, a formação dele, em processamento de sinais, filtragem adaptativa, biosinais e, obviamente, aprendizado de máquinas, no sentido amplo. Tivemos aquela palavra proibida em duas oficiais, como material, acho que era aprendizado de máquinas, ciência de dados, processamento de sinais, processamento de máquinas. Statistical signal process. Pronto, processamento estatístico de sinais. É ótimo, eu tenho os termos. Tem escribas Prof, a Academia Americana de Estudos. E, por fim, para me alongar muito, nós temos tempo, mas você sabe que vai falar um pouquinho sobre esses momentos. Diz para ele a caminho que ele conseguiu juntar aqui algumas pessoas que eu não via há muito tempo. Alguns americanos com relação para isso estão acadêmicos, por exemplo, o Isaac, que tem uma data, olha, a Ana Luísa também, e satisfeitíssimo de me responder, faz tempo que eu não vejo. Mas acho que esse pessoal aí, para os outros, tipo, o Mauri trabalhou com som, o Cláudio trabalhou com som, muito, orientou rede de som, César, então, nem se fala. Não vai falar sobre rede de som muito, mas, de qualquer forma, é uma turma que sempre me viu falar muito das suas contribuições para a ciência, para a pesquisa, e outros também. O César, porque trabalhou com biólogos. Pois bem, no momento do departamento da família, a aula Magna, foi feito aí, e o programa, programação, obviamente divulguei no NRQ, amigos, estudantes, foi em casa, do programa de estatística, do Prof lá também, e fizemos uma divulgação, o pessoal está chegando, tem gente online também. Está gravado, está sendo gravado, vai para a nuvem, vai para o YouTube, para o nosso, deixar registrado esse momento, certo? E eu vou passar a palavra para o professor. Só um segundo, professor. Tem que perguntar, né? Pronto, demorou um pouquinho, porque a gente não tinha planejado fazer a transmissão online, mas até o professor Miguel disparou esse negócio, mas ela está aí para iniciar, ter paciência de esperar um pouquinho. Mas é bom, porque realmente agradeço a lembrança, fica registrado aqui, né, como atividade do nosso programa. É importante isso mesmo. A gente está aqui meio que na periferia, vamos dizer assim, né, mas essas oportunidades têm que ser valorizadas. Todos nós sabemos disso. Centros mais desenvolvidos, né? Você tem palestras como essa, quase quinzenalmente. Né? Mas aqui é uma realidade, infelizmente, com hora que se usa. Né? Tem uma turma da engenharia elétrica, por exemplo, também, né? Sobre o Fabrício, na área de controle, desenvolvimento da área. Só me quero momento. Vamos lá. Estou muito empolgado. Eu sou à vontade. Muito bem. Obrigado. Bom dia. Eu vou falar em inglês, sabe? Porque o meu português é que eu consigo mais difícil para vocês compreenderem. Mas não tenho. Vou falar em inglês, mas lendo em português, tudo bem. Falei claro que significa, mas eu pegar mais para bem, funciona assim. Ok, muito bem. Portanto, a introdução eu vou fazer em português. Este trabalho deu-me muito gosto, porque eu sei Statistical Signal Processing e fui criado na época do Optimal Filtering, para a história do Magna, para a Aula. Durante o Covid, eu fiquei em casa, vocês ficaram todos em casa, até com a cabeça das paredes, pensaram o que é que eu ia fazer. Então, resolvi dizer assim, vou ver se consigo estender o filtro do Wiener para sistemas não lineares. Durante um ano, foi uma das coisas que eu fiz durante o Covid. Eu não quero fazer o acknowledge durante o Covid, mas não fosse o Covid, eu não tinha pensado neste problema. Foi um problema não muito tempo. E a história que eu vou contar é uma história de procura da biblioteca, da livraria, não é? Vocês já não encontram o trabalho do Manuel Barça, nos anos 60, que eu consegui encontrar o report que ele fez pensar exatamente na discussão que eu vou apresentar. Portanto,
Estamos perdendo conexão.
no meu? Nesse. Ok. Pronto. Portanto, daqui da agora não falei, sabe? Portanto, the title is an analytic solution for kernel adaptive filtering. Those of you that have worked on kernel adaptive filtering know that the methodology that is available currently in the literature is an iterative solution, like the common the KLMS, KRLS, and so on. And we are going to extend the work of Wiener for a closed form solution to nonlinear regression. And I don't know any general solution for nonlinear regression. And so this may be one of the questions. So I like to acknowledge the work of my student, Ben Colburn. This is his topic, his special topic. And also the collaborations with my former PhD students, Luis Sanchez and Ken Lee. They both are very good mathematicians that help formulate this. And obviously I have to acknowledge the funding from the Office of Naval Research. And the paper was recently accepted in signal processing and is available on the web. Okay, so just in terms of context, there are basically two solutions right now to nonlinear filtering. One uses deep learning techniques, and the other that I think it's so much more interesting from the fundamental principles because it's easy to understand the kernel, the methods that I call kernel methods. And so, obviously, a lot of people know about learning, and we all know how efficient neural networks and deep neural networks are to find nonlinear mappings. But of course, using gradient descent, the difficulty is that that thing is basically a black box. There are multiple local meaning, some of them very bad. And so we never really understand well what are features that systems are able to discover. And also, sometimes they don't work. And so, of course, the scalability of neural networks is the best we know so far. But we have problems like the local minimum, interpretation, and huge energy costs. Is one of the difficulties that this technology. The kernel methods, on the other hand, we are going to use convex optimization. It's much. Second, they are explained because kernel methods really work on Hilbert spaces. Hilbert space is a linear space. There's linear that the signal processing was countered was the theory of linear networks. You know a lot about linear networks. And so we can piggyback all this knowledge when we work with kernel methods. We can potentially come up with theoretical error bounds. Something that if we go to deep learning methods, there's no such thing. And so this ability of working from foundations, I think, is fundamental in kernel methods. And as I'm going to show you, there are analytic solutions for nonlinear problems. Analytic solutions for nonlinear problems, something that we, with neural nets, I'm glad to believe that they are not possible. But of course, there are other things that we need to worry about, like optimal design of the kernel space has been one of the difficulties. What is the kernel that we pick that represents our data? The other one is that these methods are not yet as effective as neural networks in discovery of high-dimensional solutions. And I think that this, this research that I'm mentioning today may lead to improve the effectiveness of these methods. And
there is also an issue of kernel masses is scaling up with large data sets, and that is something that we still need further understand. So this is kind of what the background that I'm going to cover. I'm going to briefly tell you what is a Hilbert space, some results in Hilbert spaces, then I go to briefly kernel adaptive filtering, and then go back to the work of Wheeler and show Parsons' solution of the Wheeler filter that is very interesting, and that was inspiration for the work. All right, so Hilbert space definition is a real values separable space. It's a generalization of vector spaces. That means that all of you that know that in algebra, you have to think that there are infinite dimensional spaces, where vectors become functions, and this is really what the Hilbert space is. And Hilbert spaces are linear spaces. And it turns out that the norm is the inner product. This is really a very nice property. They are linear. It's another very interesting property of the linearity in the Hilbert space. Simplifies tremendously the understanding. Geometries, eigen decompositions, like PCA and things of that sort. So this is beautiful. All this are beautiful properties. They are dense. That means the spaces are separable. Depending on the kernel, you have different dimensionality of the density, if you will. Universal kernel is a kernel that has infinite number of dimensions, and so it's dense. That means it can approximate any function that you want. And so, if a function converges in the Hilbert space, it converges to the same. It converges to some function also in the space. And so this is really the completeness property that is important theoretically. There are basically two ways of representing functions in the Hilbert space. One is what is called the coordinate-free representation, where we can just take an inner product between two functions f and g as the integral over f of the product of two functions. But we also can come up with a coordinate-based representation. And how you get to the coordinate-based representations is you have to define a basis in the space. Once you define a basis, then you can project the function on each one of the bases, and then you can also compute the inner product on the coordinates of the space, right? So this is just to give you that there are two representations, L2 and small L2 or little L2, and there is isomorphism between them. That means if I start with a non-coordinate representation, I can go, there's a one-to-one mapping with the unique inverse to the little L2, and I can go back to the space. So that means that this gives us lots of ways of trying to solve the problem, and we are going to employ exactly this isomorphism in the solution. Of course, we can put operators in either L2 or in little L2. That means I can transform a function in the Hilbert space to another function, right? And that transformation, also exists in the L2. Likewise, if I want to use the coordinate-based representation, what I have to come up with is with a matrix that relates the coordinates of the functions, right? And so, but basically, in the L2 representation, with L2 representation, what we have here, a matrix in the dimensions of the space. And we can combine these homomorphisms with operator. This is all things that the linearity of the space gives for free. Right? So I just would like to tell you that this is really the basis for the understanding of the solutions. But we are going to work on the special type of RHSs that I'm sorry, special type of Hilbert spaces that are called the reproducing kernel Hilbert spaces. Right? Reproducing kernel Hilbert spaces are Hilbert spaces, but they have some properties that makes life even easier. That means that if I define I can define a positive definite function, KST. If there is a positive definite function, we know by Arrow's theorem, then there is a Hilbert space that represents that I can do the representation. Properties of in RHSs are very nice because it guarantees that I don't say infinites. Okay, basically. One of the problems when we're working with functions, and you have to be very careful, even in the Hilbert spaces. But in the reproducible Hilbert spaces, that's it is signified because you have a smoothing kernel, right? That guarantees smoothness on the representations. The properties are I'm just going to do a couple of them that I think are important. Any positive definite function of two arguments can be represented by an eigendecomposition. This is Mercer's theorem that tells you that there's a sum convergently formed over space. The kernel has two arguments. If I put one of the arguments as open, that means that that's okay. The kernel centered at S, and the other argument is free. That means it can be any other point in the domain. That means that this I can represent this as a function, is an element of the reproducing kernel of space. And this reproducing property is what gives us the comfort of doing mathematics in the reproducing kernel over spaces. It says that if I have a function in my input that is the function of an argument S, I can always compute the value of the function in S by taking the inner product of the functional F with the kernel centered at S. And this property is what gives us confidence that we can do mathematics in this space. It's called the reproducing property that is beautiful. The set is this, K of S, this functional set is this, and any function can be expressed as a weighted combination of kernels. And this is really also very useful, and this is the key property for kernel adaptivity. So if I want to represent a function f, I can always think that I can obtain the value of this functional by weighting this alpha sub i's kernel evaluation. So this is really a very, very nice property that gives rise, to the what they call the kernel trick, where I can compute the inner product of two functions in the RHS is always a linear, weighted linear combination of kernels at all the points in the domain. Okay, so this is just to give us an idea of properties of the Hilbert spaces and kernel spaces, RHSs. And an example of this application is for kernel adaptive filtering. We know that, for instance, LMS algorithms do send a very simple way of training parameters over the model, right? But for ZZ and has to be constructed in the linear. What this linear means is that the output of a linear model is always in standard linear. Right? And if you want to come up with outputs that are not in the standard linear, forget about using linear systems. Right? And so, so the advantage of neural nets is exactly the output of a neural network is not restricted to be in the standard input. And I would like to write exactly the same thing by using this idea of the kernels. And so the idea is very simple because I can come up with a nonlinear function and any nonlinear function to arguments like the neural network is one possibility, but if I restrict this mapping to be a kernel, that means that, for instance, in my kernel, the variable space is defined by the Gaussian. What I mean is that I have my data sample A. I map it with a Gaussian function to the reducing variable space. And what this means is that I've created a Gaussian in the RHS centered at the point. Right. This is really where is the nonlinearity is to go with the Gaussian. But then in the reducing variable space, as I told you, is a linear space. So I can use all properties of linear methods to compose the output of my field. And how can I do that? Just by using the property that I told you that any function in a reducing variable space is a weighted combination of kernel evaluations at the point. And it turns out that for adaptation, for optimization, this alpha that you see there is nothing but the error that particular sample presents when you compute the nonlinear of the kernel. So you look at the error, and you end up with a representation, a functional representation of your model. Right? Very simple. But notice that normally for linear filters, we select the order of the filter like L, number 10, order 10. The problem with this kernel adaptive filters is that the sum grows with the number of samples. Okay. So this becomes very difficult. Right? It's one of the difficulties of this methodology. Is that you are composing functions, but you need to update these functionals with every sample that you are having. And you need that to really come up with very precise outputs. Right? And so this is one of the shortcomings. If you are interested, I wrote in 2010 a book with my former students and Professor Simon Haken on kernel adaptive filtering and comprehensive introduction. That is still best push, in my view. That explains how the design kernel adaptive filters. That's more than 2,000 citations. It's really planning for the easy. All right. Okay. So I'm not going to talk more about kernel adaptive filters. But I'm going to go back to the foundations of the optimal modeling. Work of Norbert Wiener that solves the minimum mean square error estimation problem with a linear model given some input and desired function. So you give me any input and any desired function, and Wiener was able to come up with a filter that basically solve, is optimal. But of course, you work on continuous time, and if you want to come up with this this integral equation to solve for the parameter, right? So it tells you the cross correlation function. That means the product of the input and the desire is equal to this integral between two limits that not necessarily need to be zero and infinity, but can be shorter intervals. But it's just this Fredholm equation that it is an integral of the parameters, right? This is a functional, and multiplied by the autocorrelation function of the input. This solution is very difficult to estimate in continuous time, but Kolmogorov proposed, said, well, this is complicated, but if we are in the digital domain, this becomes trivial. And this solution is the one you probably, if you have heard about it, so that is one that you learned. That we have a filter with a certain number of lags, the order of the filter, L. We have an input signal, a desired response. You compute the autocorrelation function of the input. You have this matrix. The autocorrelation function is, as you can see, is symmetric, positive, definite, and so this is really a kernel. If you think about it. The cross correlation factor is simply the expected value of the desired with the input. This is the cross correlation factor, and the solution becomes a Magna function. Right? This is very well known. Optimal. Don't know this solution in 2-bit. You are not the single processing. Right? This is my test. And it's very interesting that the error is orthogonal to the input. This is very nice. It is the minimal norm solution. All right. So, and of course, real filters for discrete time are very simple, and we will use this solution. But it turns out that Manuel Parson, also a very, statistician, he came up with a different interpretation of the input that I found very, very intriguing. I'm going to tell you why. So he presented a solution of the filter on a reproducing granular space that is defined by the autocorrelation function of the signal. As I said, the autocorrelation function that matrix of values, positive, definite, so it's a kernel. So there exists a reproducing granular space that has autocorrelation function as the kernel. The beautiful thing about this is that it depends on the statistics of the input. Remember that the kernel and the filter lives using the Gaussian function that is fixed, right? And you can also define reproducing granular spaces that are data. And he showed that this autocorrelation, this reproducing granular space defined by the autocorrelation function, requires three steps to be useful. First one is that there is a congruence mapping between the linear span of the time series, signal that you receive from the world, and the span of the reproducing granular space. This is a very important property. They have to be congruent. Second solution, the second step is you have to find the representation of the cross covariance function in terms of linear operations on the autocorrelation curve, right? Because you have the kernel function, and so you have to represent the desired response in the space. And the solution then becomes simply the minimum norm solution in the reproducing granular space defined by the autocorrelation. So it's just the minimum norm solution. So well, right. But remember that 3 steps is the first thing you have to do is you have to show that there's a congruence between the span of your time series and the span of the functions we are talking. And the second one, you have to represent the cross-correlation function. You have to project it really to the space. All right. The congruence mapping is a very simple idea. Is a mapping function that preserves inner products. That's the only thing. Right? So that means that if I compute an inner product in the one RKHS H1, and if I do a mapping, this mapping psi is a congruence mapping. If in another RKHS, I can, this inner product that I obtain, this one is equal to this one. That means that the inner product in H1 is equal to inner product of this psi on the function. Right. Okay. And so he proves that this is okay. And so I'm going to show you the constant solution for the inner problem. So you have to compute the autocorrelation function of input. You have to represent desired response in this space, and this is just simply, you have to project the product, the expected value of Z, and that is the desired response on the input space. And then the solution is just given by an inner product. Right? And if you want to compute it with the tools that I have there, what you have this quadratic function. Quadratic form. It's just the inverse of the autocorrelation function that is pre-multiplied by a vector that is the transposer of the input, and post-multiplied by the okay. This is computational wise is worse than the winner solution. But notice the winner solution is here, right? Because what is R minus 1 times rho? Is the right? So if you can a priori compute W star, you don't need to have this double sums. But this to me was, when I saw the solution, I said, like, I'm sure I can come up with a non-linear representation of this solution. And why am I so confident? Because the beauty of a coordinate-free RKHS is that once it is formulated, it can automatically be applied to any other target. I knew that. It took me about 6 months to find out how to use this thing, right? This is given. This is the beautiful thing about the differential space. If you find a solution in one of them, you can apply exactly that to any other. And this has beautiful properties. I like, different neuroscience. That can work with spike trains with the same code that I use for continuous time sequence. Why? The only thing that matters, instead of using the Gaussian function, I use another mapping function that works on spike train. So that I use orthogonal filter, I can apply it to continuous mapping signals or the spike train. Same solution. It's beautiful. And so I knew that there is the possibility of creating an all-linear filter. I simply do not know what we can think. All right? And so this is the start. So let me just go back, and I'm going to just tell you. The solution has to be this form. It has to be this form. Okay? The only problem is I have to, if it's not linear, I cannot write the projection as easy as this. Right? And I have to guarantee that the span of the functional that I'm going to use has to be congruent with the space of my data. we expand it to fancy, because this is what I want. All right? So this is really, so I thought that there is a universal limit filter. I simply don't know it yet. All right? And now I'm going to tell you how I do it, right? Be prepared that it's a little more complicated. Why? Because I know that if I want a non-linear filter, I cannot work in the input space. I have to work on a projected space of it. So it is what I thought about since I have my Gaussian, this is what I would like to do. You reproduce incredible space defined by the outer correlation function of the projected functions that is congruent with the span of the times. This is what I want. Okay? And so what is to be more formal means that I'm going to write what are the functions that I'm talking about. So we are going to define a set of functions of f capital X that is done by, I have to have two arguments, right? I have to have dimensions, and I have to have time. So you have X and T, you know. And so it is going to be the cross space, you know, the product space of my data and the time. And then it's a finally, in the family of finite second order, I have to have limitation that I can only represent, you know, random processes that are finite variance. And so the set is the response to set of random variables that can be written as this double sum weighted combinations of, you already saw the weighted combination before. They are going to be weighted combinations of some scalars that have two indices and my functions in my functionals in RHS, right? And so, and W and MW are the dimensions of this space. Okay. So this is set of objects that I'm going to work with. They are functions of positions of random variables in the RHS and also of time. And then if I want to compute the product in L2 of two functionals Q and V, I'm going to try to represent, I want to represent them an expected value of Q and V in some space. I should have put there the representation of space. But this basically, since I have double sums in my functionals, and I'm going to compute them in the product, guess what? We're going to have 4 summations right? And I'm using this representation in Aula 2 because I'm representing this, on coordinated space. And so basically what you are going to have weighted combinations of two arguments, A and B, right? Two constants, A and B. And then this expected value of XL, XTJ with another functional, FXK, XTL. And so this is going to be, I'm going to represent this by this operator U that has 4 arguments, 2 time arguments and 2 special arguments. Right? So this is a little detailed, but the methods are, the formulas are basically the same, right? And so I have to show first that this operator, is a positively definite function that defines a reproducing character space. We prove this, and I mean it's very easy by construction. We can prove this that is congruent with L2 weapons, and this is the important combination, the property that I would like to present, and that is the reason why I'm writing this in this explicit form, just to simplify this congruence. I can find this in different ways. So what this means is that then the last thing that I would like to do is to represent the projection of the desired response in the space of the functions f(x), the arguments that I talked about, as the expected value of the desire projected in the space of Magna. Right? And then, if that is the case, the the minimum mean square error solution can be written also as the inner product between rho in the space with x defined in the H of U. And so that means that I'm going to have my quadratic form exactly as possible. Okay? And this works, okay? But when you go into the detail, you find out that these functions f that I defined, okay, are just that one sample as an argument. And that is a limitation, because what we would like, looking back at the data solution, I would like to operate with multiple functions. And so basically what I have to do is I have to, instead of working with a scalar in the argument of the functional set, it has to be a vector of dimension. And now this solution has no limit. Okay? The problem is this, I wrote this mathematics, very beautiful, but the issue is, how am I going to compute U? Right? I know that U exists, but I'm going to compute it from data. Right? If I cannot compute it from data, that's not it. Mathematically valid, but I need to do this on data. And this is where, Kelly, my students is truly engineering and all that. Now we are going to approximate the Gaussian arrangement. All right. So we know that the Gaussian RHS is a reproducing kernel over space. Now that I denote by H of G is infinite dimensional, and it's universal because it is infinite dimensional. But the point is, I would like to operate, because I have my formulas in little L2, right? So I would like to be able to use the formulas that I presented to you. And so basically what we did, we just, Gaussian function is a beautiful function. We know that there is a polynomial decomposition of the Gaussian. So the polynomial. Remember the polynomial? Right? If you have infinite number of them, you get the Gaussian. Everybody okay. I get it. roughly a Gaussian, right? But it's finite dimensional. And that means what? That if I approximate the Gaussian by the mid polynomials, right? We showed that this inner product, where the fees here are the mid polynomials, is a positive definite point. So it's also an RBHS, the finite dimension. Okay. And the dimensionality, you know, I have to say how many terms of the that I want with my approximation of the Gaussian, and that is the D. Okay. All right. So with this, what happens? I can now I go a little bit faster because I think I already told you everything. So basically, what you have your data, right? I would like to go to the space, the Hilbert space of the Hermite, finite Hermite polynomials that I represent the H of B, right? And so I would like to approximate the autocorrelation function if I want to write the autocorrelation function at H of B. How can I do that? Well, I map the data to the RKHS HB as functional, right? And then what I'm going to do is I'm going to work with the vector function with window L, and so I have this big matrix with columns are emit extensions, multiple emit extensions that computed at T. This is at T minus 1, and so on. And so I have this big matrix that I can effectively work with a very long vector, right? And it turns out that this HRD, if I look now at the columns of the mid polynomials over a window of L, this is also a positive definite function that defines another RKHS. That is the span. This is HRB is the span of the equivalent to the span of the autocorrelation function, but now in RKHS. Okay. And so my U function, this operator on that RB, is an operator that has space and time coordinates. U1 and U2 are the dimensions of the Hermite projections of the Hermite polynomials. Okay, so I have here space information computed at pairs of samples in time, like S and T. And so in RB, in the HRB, this is how I can represent this function. All right. And of course, if I assume stationarity, I don't need to have this rank 4 tensor. I can work a rank 3 tensor. So I just compute T and T minus tau, right? And so this simplifies the computations. And this is my representation of the operator over tau. And we can also come up with a matrix representation of this 3D tensor in the product space of T and L, and for values at the same time appear in the diagonal of this matrix. But it just gives you an idea of what is it. And so the proofs that we have to do, what are relatively easy to do, because I told you already this HRB is a Hilbert space, general Hilbert space, is that I can compute this kernel on U, on the Hilbert space defined by the U function in this form. This is This is the quadratic form that I showed you, right? You have the matrix of that represents the expansions of the projected data. And this is another element in the space multiplied by U. So this is the quadratic form. But now this is computed, right? Okay. All right. So there's a isomorphism between HU and HRD. That means that inverses always exists. All right. So I don't have to worry about how to do it. And then the analytic solution, I'm going to show you how it compares with. So we saw that we compute the auto-correlation function in the input space. For non-linear space, here is the equivalent auto-correlation function, functional, right? Remember that there's a function of dimensions in the reproducing kernel and time samples. So this is this representation. The functionals are functions of time. It's like Coulomb operators. So you have the functional of time in the RHS, even by how the operation function changes. All right. So I have also to express the desired response in this space. This is easy, right? Because it's expected value of this with the finite dimensional Hermite polynomials. So it's V, right? And so this exists in HQ. This is the solution that I presented to you before. And this is the representation that now I can. That is basically the same form, right? It's a quadratic form. Except that now you have here space-time autocorrelations. And here you have nonlinear projections of the input vector or the polynomials. That's it. Okay. So this is analysis. So for the next minutes, I'm going to show you how this works. Okay. How many people? How many people? Sorry? I lost how many people will be on this. So this is easy. It's a lot of detail, but I hope I gave you the transition concept of the same. Right? You understand the winner solution, you should understand. Okay. This is the function. We call this functional Riemann filter. And it is a closed form solution. It's just the minimal norm solution. You project your data, the desired response in the space that you construct. I'm talking about projection. Okay. And all this construct. All right. Okay. There is a relation with corruption that I'm not going to talk about. Let me just tell you that the beautiful thing about this, I know before I start, I know what is the error. What is the error? MMM solution is the power of the desire minus the inner product, in the projection of the input space, right? So it's going to, I know that this is not linear MMC solution. This is the solution. If I can estimate this, and estimating this means how many Hermite polynomials I'm going to use, right? I can just set this as a parameter. This is really the training solution after I operate with this from data. And theoretically, I may see the difference between the two is this. This is 10 to the minus 12 errors, 10 to the minus 14 errors. So this is almost perfect. Okay. Notice that test MSE, this is the theoretical MSE goes down. The test MSE goes down, but then stabilizes. So the system is stabilized. Some experimental results. This is what I think is very interesting. We came up with a very complicated signal. This signal has nonlinear transformations at every sample, and the nonlinear transformation changes from sample to sample. And I have learned this system. This still is easy because I have, it's different nonlinear functions, but the argument is just one sample. Okay? But here it is. So I'm showing here the evolution of the weights. Weights now are time function, right? And so I'm telling you the time, the weight, the optimal weight functions, how they change over time. All right. This is this is here you have no noise and you have noise results. This bar, this shaded area is the support of the But this is very interesting. So these results here are, so we created this signal with the 4 delays, right? Or with 4 samples. So the window is 4. And I'm giving you here 5 functions. This is the support of the data. And you see, here you have 2 curves superimposed in each other. One that is the true signal and the other the approximation, then they coincide. What is interesting is that I created a filter with 1 extra weight, and the extra weight goes to 0. Because in some data that's not there. No representation, so the filter goes to 0. Even with noise. Now I add the noise to the signal, and you basically see that touring, so it's very robust. During the time that I'm sampled, this is very robust. Then I have many more examples, but I'm not going to show you. This is Lorentz prediction. I think it's interesting. Magna glass prediction. Let me just tell you the comparisons that we did, because there's many other filters that we are comparing. We are comparing the LMS, KRLS, Gaussian processes, kernel regression, and a joint space Gaussian model. And as you can see, And the WF here, you only, FWF only has one sample, right? Representation of the functions of one sample. And it works very well, like kernel regression. If we go to multiple samples, and this is making to us, we are always the best performing. Sunspot prediction, this is a realistic time series, you know. This shows that the FWF really memorizes things. So when we go to D equals 3, D is how many samples are constructed first. F, and here the best result is when D is equal to 2. So the functions constructs of 2 samples only, and it's better than any of the others. In terms of test time and training time, of course, we are creating a space. Our space is more complex. And in training, we have a term that is Q on the dimensions of HQ. But this K that you see there is just 1, 2, or 3. We did not find any example that any functions with more than 3 samples. And so you see that the training computation is very similar to linear solution, right? R minus 1 times P. So you have the square of the dimensions of the space and the radial length and the number of samples. But look at the evaluation. It's independent of the number of samples because it's analytic solution. And so you see that it's flat. And this, by the way, this is a very big scale. All right. So conclusions. We could anticipate that this was possible 4 years. It's not easy. But now I think we have the first full-form solution. All in all, but this space is very, very peculiar. It contains the statistics of the data. This is exactly that gives you the ability to have weight functions that evolve over it. So this is really a different way of thinking about it. Because I'm learning this from the data. I don't need to do the tweaking that everybody does. You have to find what are the terms that you are going to approximate. Of course, we chose a finite dimensional space to do the calculation. But notice that we are doing, is we are doing eigendecomposition, right? So we don't need very large number of kernels. Right? And I'm not going to talk about because tiny. But if you address it, we are still developing. Okay. But this opened up a window that I think really had to bring all of that. So we want to solve the recursion to the cheese. We can implement it because human states. We have a very open space, and we don't need to have neural networks. We have to have a great network to prove it. Here from scratch. From scratch. We create a technique. Okay, so I think that this will make from the criminal that's and how to All right, thank you very much for your attention.
Obrigado, nosso Príncipe. Foi muito didático, em vários sentidos. Primeiro, eu fiquei aprendizado de Magna, não é só pai. É de piloto. Já apareceu aí no slide. Né? Mas, obviamente, que eu coloquei o jeito para de sinais. Quem tem essa base de calçamento de sinais, ouviu falar de divina, né? Pedro divina. Né? E já existe uma solução, né? Eu vou começar das perguntas aí. Né? Eu conheço essa fio divina, tem uma solução do kernel fechada, né? No sentido clássico, né? Mas ela, por exemplo, não escalona, o estereótipo dela é péssimo. Na verdade, ela só tem aplicação teórica, conceituação teórica.
Exato, qual é? Como é que você tem que estudar?
Porque é diversão de campo.
E a diversão de campo. E é que está aqui é tratado, é que essa solução do não tira vantagem da estrutura das eigenfunctions. E sem isso, meu amigo.
Só não tem a forma mais prática, você tem que definir também a função de quê? Tem várias opções. Nessa moda da estudo, eu já estou definido. Só escolhe um outro nome que permite, na versão aproximada. É sempre ela. Sempre ela.
Mas, não se esqueça que isso é o passo intermédio.
Sim.
Depois eu defino no último projeto em Kernel Open Space, em que tenho informação sobre a estatística das funções que estão projetadas no algoritmo. Isso é identidade.
Sim. Mas é muito rápido, né? Uma pergunta, eu vejo algumas aplicações, eu vejo o pessoal da velha televisão. Então, isso é uma teoria que torna linear no espaço de Deus. Essa transforma o sistema não linear, mas você tem várias aplicações, identificação de sistemas. Todos os órgãos de identificação de sistemas, né? Pode usar aqui essa teoria. E começa com vinha, dá uma solução fechada, tem matriz, tem uma parte que é possível também. A estimação é possível. É possível de fato na prática.
Todo mundo consegue me ouvir? Todo mundo consegue me ouvir aqui?
Sim, claro.
Ah, tá. É verdade.
É verdade. Olá, pessoal. Bom dia a todos. Sou Marcos Vinícius. Eu trabalho aqui na oficina também de pós-graduação, mas sou professor da UFES. Bom, é muito legal o seu trabalho, professor. Eu achei muito interessante porque eu leciono lá na UFES sinais e sistemas, análise de sinais e sistemas, e um dos assuntos que eu leciono é filtro de Wiener. Então, eu leciono tanto o filtro de Wiener como o filtro de Kalman. A minha dúvida, professor, é se já foi feito testes comparativos, por exemplo, a abordagem do filtro de Wiener, esse método, usando o Wiener para sistemas com modelos de kernel não lineares, no caso, ele só aproximar o modelo quadrático, né? E aí, meio que o espaço de Hilbert separa e mantém a linearidade, né? Comparativos para tratamento de imagem, que os exemplos aplicativos que eu utilizo de graduação é para a aplicação do tratamento de imagens, aquela imagem clássica da lenda, né? Aí eu gostaria de saber se você já fez estudos dessa abordagem para tratamento de imagens, para filtragem de imagens.
Sabe que a imagem para mim é um sinal por dimensões.
Exato. Mas se você for colocar imagens, por exemplo, para sinais gaussianos de variância diferente, vai ter um trabalhozinho para se fazer, porque isso interação entre eles, né?
Mas, é verdade. Isso é verdade. Claro que o meu Hilbert Space do operador U tem a população de dados. Portanto, é Spatial Correlate. Primeiro, você pode utilizar isso diretamente, essa solução que está diretamente. Quer dizer,
Tá. E a comparação com métodos como, por exemplo, o vertical? Você já chegou a fazer comparação? São diversos diferentes.
não, já nós temos um filtro, calma, já no Granules. Portanto, eu posso utilizar esse trabalho e aplicá-lo à solução, full source solution. Mas pá, então, um filtro
Mas o senhor conseguiu valores melhores que o filtro de calma com esse método? Inclusive a aplicação do filtro de calma da UNE? Interessante.
nós estamos a fazer uma perdão, calma.
Bem interessante. Obrigado, professor.
Professor Príncipe, muito obrigado pela apresentação. É um resultado bem interessante, super recente, né? Super recente, sendo publicado agora este ano. Bem, eu sou César Lincoln, né? Sou professor do Departamento de Computação, PPGETI, e pesquisador também do PPC e do MIT. E filho da casa, né? PPGETI, aqui, orientado pelo Guilherme. E bem, esses métodos de kernel, eles são super interessantes, né? O Guilherme fez a gente estudar eles desde a graduação, né? Antes da formação, a gente já estudava em todos os formatos.
Então, deve agradecer aí, né?
Exatamente. E acabou que no doutorado eu me aproximei mais dos modelos de processos gaussianos, né? Que tentei juntar a abordagem de kernel com a abordagem gaussiana. E teve alguns análises, alguns passos apresentados na apresentação de hoje que foram muito interessantes. Eu achei visto na literatura de processos gaussianos, a parte de filtragem bayesiana, né? Os trabalhos da economia do professor Sino Sartre, lá da Finlândia, que tem um livro muito bom, incrível, filtro de calma internalizado, com a abordagem bayesiana, então tem conversado super interessantes. E a minha questão era mais relacionada, e alguns trabalhos um pouco mais recentes, assim, nos últimos 5, 10 anos, para o pessoal de GP faz solução recursiva, eles utilizam aqui teoremas de unificamento, Kint, né? Que faz a composição espectral da covariância, da função interna, no caso estacionário, né? E aí eles usam planos de features, né? Eles têm outras abordagens que eles fazem, e essas abordagens escalam muito bem, mas elas não costumam ser uma aproximação tão boas. Fora essa limitação de o kernel precisar ser estacionário. Eu queria saber algum comentário nesses dois aspectos. Assim, a gente ter uma aproximação mais poderosa e a gente conseguir escapar da estacionalidade. Eu vi que você, em algum momento, colocou a estacionalidade, mas você pode tirar, né?
Veja, qual a necessidade, né? Então, a vantagem destas divididas é que impõe condições para a solução. Tudo o resto são aproximações. Nós aqui também sabemos como aproximar um processo não funcionário. Usando real-time updates da Delta Collection. And so basically what this means is that the new operator is going to be continuously up. And the interesting thing is we could link this new operator with the kernel PCA. And now we have an online update of the new one. That means that we are tracking changes of the item functions while the system. So it's very interesting. But this is future work. a priority and we have results that show what this is possible. So, yeah. But to me, the trick that it's work idea is it's on the kind of features.
Obrigado pela apresentação, Gelman, professor lá do Instituto Federal. Voltando a essa questão da não estacionalidade, né? O KRS também se baseia no sistema estacionário e tem também a reversibilidade e não consegue, muitas vezes, fugir à não estacionalidade. Aí, nesse caso, teria algo a mais para evitar?
If you go very fast, forget it.
Amém.
There is the only way if the data changes very fast. What you have to do is keep right? Mixture effects. This is what I use. But it turns out, that the kernel, the recursive updates to fix point. So that thing is much faster than less. But still, they can change it very fast.
Outra pergunta é em relação a duas coisas. Se for analisar a questão do objetivo, a solução, né? E se como solucionar a questão overfishing, eu vou tentar
Pode. The issue of overfitting is a problem. This is the reason why I think that the overfitting helps with my view with new costs, new infrastructure. But it's a long story. But the idea is universal running machines are nice, but the point is we always have finite amount of data. So it's a necessary condition, but the model is not sufficient. How to come up with the sufficiency is associated with market. Everything, in RHS is that you have geometric understanding. So what you have to think is that overfitting is associated with the volume of the solution space. And what
Pergunto para ele, não vou exatamente para ele por e-mail, ele é bastante acessível.
não inventa não.
Para ele é acessível, ele responde mesmo. Então manda para o Badong responder.
O Badong não já responde.
Obrigado, pessoal. E o pessoal do MQ aí da folhinha, todo mundo assinou aí a presença? Não fui eu que cobrei, eu não professor lá.
Esse copo.
Vocês acompanham o que sobre isso?
E aí você fica no definitivo e faz a comparação só com o índice de causa de 50 reais. É o vídeo aí eu vou fluir. Aí eu pensei
Não, foi mais assim, acho que
legal, imaginar como você
aí agora ele está fazendo.
Não, estava fazendo.
Mas a vida, não, mas Só experimenta. Depois vai perdendo uma luz. Não, mas ele vai terminar.
Isso é uma maneira de ventilar, só se faz.
Ele é muito aí as alternativas agora ele
Vocês atrasados, são pessoas fazer isso aí? Não, porque eles estão tentando ir para outros veículos diferentes para o que acontece? Poderia, ele já quer sair. Essa é a minha área, professor, mas como fazer? Ele não vai fazer mais ele não quer andar para aqui, ele vai fazer pesquisa, ele não quer fazer ciência. Mas por que não estamos usando o cérebro, né?
Mas eu acho que
Vocês entraram para terminar. Aí o cara já ia sair. Aí tem que fazer mas eu achei interessante que eu fiz isso. Essa aplicação de quer. Aí eu só utilizo uma porta de quadrado do ele cai na realidade porque não consegue crescer. É só da projeção. Isso faz esse passinho para provar a realidade. Mas isso agora consegue. Você não é tão linear, mas é fica colaborando com esses fazer parte do programa aprendendo depois fazer um contrato X, saco, porque sempre são coisas diferentes. Então, Isaac, você precisa em relação os alunos só aí eu vou na aula do almoço. Eu tive todo dia de parceiro de dedicado. Eu tenho um saco para fazer legal. Aí eu ia e você com ela dele, ele tá achando que ele tá assim. Você pega só valorização do sucesso. Para fazer só computador do lado. Proposta lá. Você ia só pensar no ponto. Quer que vá para fora?
Não é boa opção. Tu fez isso?
Tô fazendo. Aí só que aí, mas como é que vai ser? Mulher vai embuchar e eu vou para fora, vai deixar a boca sozinho.
Vai junto, cara. Ó, cara, isso aí não é impedimento, não.
É porque ela ganha muito bem de trabalho.
Ah, sim. Aí isso aí é.
Aí ela ganha muito que eu ganho. Só mentira. Eu vou indo. Eu tenho que ter um compromisso aí.
Valeu, obrigado aí, cara.
Mas eu sei que o senhor também tem interesse em trabalhar com ele faça
Eu você que... Ah, gente,
quando chegar aqui, aí eu faço umas aplicações com outras heurísticas aí. Eu tenho umas heurísticas.
nem o...
Eu tenho umas heurísticas de bolso aí já prontas.
Sim, também. Eu estou fazendo vários testes com a prova aí.
Oi?
Tem alguns alunos que estão... Espero que defendam. De mestrado, eu vou ver lá se dá certo chamar para a banca aí.
Pronto, aí eu tenho...
Foi tudo.
Deixa eu ver. Segura assim uns 200, né?
Eu fiz isso aí. Quase que eu quero apertar aí. Não tá respondendo, não. Eu nunca vi isso também, né?
É o Windows se rebelando, tá com você também com o meu notebook.